this chapter we're going to look at topics related to measurement. In this lesson we're going to look at converting between linear, area, and volume scale factors.
Okay, hi everybody. So now we're going to be converting between linear, area, and volume scale factors. Okay. Now you've already had a little bit of practice with this in a couple of the previous lessons, but we're going to talk specifically about it now. And just some things to note here. We cannot directly convert between an area scale factor and a volume scale factor. Now, that's not 100% true, that statement. Yeah, we can. It's just a little awkward. And so we want to save you that kind of awkward step there, okay, with some powers there that you might not be used to. And we're just going to suggest that you got to go back to the linear scale factor first. Okay, and we always want you to do it that way. So now, let's think back here. A scale factor that is greater than one will result in an enlargement. And a scale factor that is between 0 and 1 will result in a reduction. Okay, so getting bigger, and if it's the scale factor looks like that, it's going to get smaller. Remember the relationship here? The linear scale factor is the length of the new object compared to the length of the old object. And if you want to go to the area scale factor, you simply square the linear one. And if you want the volume scale factor, you cube the linear one. Now, then a little note here. If it asks for the scale factor, it's going to be referring to the linear scale factor. Okay, that's going to be implied. They won't say it outright. They're just going to expect that you know what it is we're talking about. Okay, so this is all familiar ground. We've done it with a couple of lessons already. Now let's take a look at some questions. Okay, so let's take a look at this question here. First one says, the surface area of a globe is 2,827.4 centimeters squared. And the surface area of a larger globe, so it's been enlarged there, is 70,685.8 centimeters squared. What is the surface area scale factor that could be applied to a smaller globe to produce the larger? Okay, so our area scale factor is going to be the area of the, let's say the large, okay, because we're trying to produce the large one, over the area of the small. Sorry, I had a spicy chip just before I started this, and so I'm kind of dealing with this spice right now. Anyway, the surface area is going to be 70,685.8 centimeters squared over 2,827.4 centimeters squared. I'm asking you for the area scale factor, so I'm going to be comparing the areas. So here we go, 70,685.8 divided by 2,827.4, and we're getting an answer that's almost perfectly 25 here. Okay, that's approximately 25. So now, what would the corresponding volume scale factor be? Okay, well the first thing we're going to do is we're going to take this back to the linear scale factor, and the linear scale factor, remember, will be the square root of the area scale factor. So that's going to be the square root of a number that's approximately 25. So I know that my answer is going to be basically 5, but I'm going to go here anyway and take the square root of that answer, and it's 5.000. Okay, so that's close enough. That's approximately 5. So if we want the volume scale factor is going to equal is going to equal the linear scale factor cubed. And so that is going to be roughly 5 cubed. So I go here, and I know this isn't exactly 5, but I suspect it'll be close enough to 125. So this is going to be approximately 125. Okay, and so there you go. That's the volume scale factor comparing these two globes. Okay, let's take a look at this next question here. Bit of reading. It says the volume of an Olympic-sized swimming pool is 88,263 cubic feet. A swimming pool wants to build a practice pool similar to the Olympic pool. The club decided that their pool will be 3,269 cubic feet. They want to paint their pool, including a plastic cover, with winner's blue paint, just like the Olympic pool. So if the Olympic-sized pool needed to cover a surface area of 11,263 square feet, how much surface area will the club have to cover? Oh, wait. So basically, we have the ability to compare the volumes of these two. What I need to do is come up with a comparison for the surface area and then use that to get the actual surface area of the pool that this club is making. Okay, so first of all, we're going to take a look at the volume scale factor. Oops, I don't know why I wanted to put a C there. That makes no sense. Okay, scale factor. And in this case here, this is going to be a reduction because we're going to start with the volume of the small pool compared to the volume of the Olympic pool. So the small pool is going to be 3,269 cubic feet, whereas the Olympic size pool is going to be 88,263. And I'm not going to bother fighting. Oh, sorry about that. I'm not going to bother fighting with that. I will make that 3,269 divided by, 88,263. Okay, well now I get a repeating decimal there, so that should convert nicely to a fraction. 1/27th. 1/27th. That's my volume scale factor. So now I'm going to go back to the linear scale factor, which is going to be the cube root of the volume scale factor. So this is going to be the cube root of 1/27th. If you just think about that for a moment, you'll probably figure out that that's going to be 1/3. Okay, so there's my linear scale factor. So I took it back kind of to the first one, the original one there. Now, the area scale factor is going to be the linear scale factor squared. Okay, so that's going to be 1/3 squared, which will become 1/9. And that's what I've been fighting for. This is what I wanted to get to. Because now what I can do is I can convert the surface area of the Olympic pool into the surface area of this smaller pool. So that's going to be the surface area of the Olympic pool. We're going to multiply by the area scale factor, and that's going to give us the surface area of the smaller pool. So here we go. 11,263 square feet multiplied by 1/9 is going to equal the surface area of that small pool. So now let's grab the calculator. Let's do it. So 11,263 divided by 9, and we get, I want to make sure that I plug that in right. I was expecting a prettier number, to be honest with you. 1,251.4 square feet. That is the surface area of the smaller pool. And there you go. Okay, so before we get into the next question, let's just read this little note here. Questions will not always tell us which conversions are needed, so you're going to have to learn how to read the question to determine what they're asking. This is an important skill kind of across all of math when it comes to solving problems. And it's not easy, so if you struggle with it, I don't want you to feel bad about it. It's just something that requires work, requires practice, okay? So the first step here is we've got to determine what is the question asking for, what is the information that's given, state what conversions need to be done, okay, that need to be used, and then use the formulas to complete the necessary conversions. Okay, so let's jump in and take a look at an example. Okay, so our first question here says, an eraser company makes large erasers with dimensions 4 centimeters by 3 centimeters by 2 centimeters. They find that there is a market interest for even larger erasers, so they do makes an extra large eraser with dimensions 24 by 18 by 12. Okay, one of the longest rectangular faces of an extra large erasers is to be painted. Sorry, one of the longest. I read that wrong. Is to be painted with a logo. What area scale factor can they apply to the large eraser to produce the logo on the extra large eraser? Okay, well, we're kind of lazy here, so I'm just going to compare the corresponding dimensions here. Let's compare the length with the length. So to get my linear scale factor, okay, I'm going to compare the length of the large to the length of the extra large here. Now, bear in mind that the extra large one is going to be the new one, so it's going to go on top. So this will be the length of the extra large over the length of the large. So it's going to be 24 centimeters divided by 4 centimeters. and we see that we're multiplying by 6. That is our area, sorry, that is our linear scale factor. If that is the linear scale factor, then my area scale factor is going to be the linear scale factor squared. And so this is going to be 6 squared, or 36. So that's what we're looking for here. So what area scale factor can they apply to the large eraser to produce the logo for the extra large one? It's going to be 36 times larger. Okay? In terms of area. Now let's take a look at this one. If they developed a life-sized eraser that had the length of 96 centimeters, and a life-sized eraser, I'm not sure what that means, and had a length of 96 centimeters and wanted to know the volume of rubber needed to produce such an eraser, what volume scale factor could be applied to the original large eraser? What volume scale factor could be applied to the extra large eraser? Okay, so these are two different questions here. So let's take a look at comparing the large one to this really large one here. So our linear scale factor, if we take and compare the two lengths here, so the length of, let's say, the extra large, let's call it life-sized. Okay, we'll call it the life-sized compared to the length of the large. That's going to be 96 centimeters divided by 4. That 4 centimeter one doesn't seem quite so large anymore. So 96 divided by 4 is equal to 24. So what that means is, in terms of the linear scale factor, to go from the large to this what they call life-sized one is 24 times. So our volume scale factor is going to be this linear scale factor cubed. Okay, that's going to be 24 cubed. And on my calculator, when I go 24 cubed, I get 13,824 times larger. Now that actually makes a fair bit of sense. These numbers, once you start to look into volumes and you start cubing things, these numbers grow really, really quickly. Now if we take a look at the linear scale factor from the life-sized and we compare that to the extra large one, well, in this case it's going to be 96 centimeters compared to a length of 24 centimeters. Okay, so 96 divided by 24 is 4. And now the volume scale factor to compare these two will be the linear scale factor cubed. Well, that's just going to be 4 cubed. That's just going to be 64 times larger. Okay, and so those are the two scale factors they're asking for. So in this question we read that Maggie has scanned an 8 by 10 photograph on her computer, and she'd like to increase the area by 44%. So, okay, so we've done a question similar to this, so we're just kind of going to build on it here. Determine the area scale factor and the linear scale factor. Okay, well, if we're going to increase the area by 44%, okay, remember what that means is our area scale factor, and I know we talked about this in a previous lesson here, this is going to be 100%, okay, plus an additional 44%, which gives us 1.44. This is what we're multiplying by. That is the area scale factor. Because remember, it's an increase in the area of 44%. So we start with 100% of the total of the area, and we add 44% of it. So now, to get the linear scale factor, that is going to be the square root of the area scale factor. So the square root of 1.44. And the square root of 1.44, I suspect, is going to be 1.2. Just wanted to double check that. Okay, so the area scale factor, and explain why these are different. Okay, so what happens here is the linear scale, okay, the area scale factor, or sorry, let's say it like this. Area is the result of the product, okay, of the product of length, oh, and I'm probably going to get off the screen, no, length and width. Okay, length and width. If each of these, okay, if each of these is multiplied by the linear scale factor, okay, if each of them is multiplied by the linear scale factor, then the area is multiplied by the linear scale factor squared. Okay? In other words, think of it like this. If area is equal to length times width, and then I've got this new area that is the length by the scale factor multiplied by the width times the scale factor, then what we did here is length times width multiplied by the scale factor squared. That's why they're different. Okay, that's why that turns out to be different here. And this ends up being the scale factor for area. So to determine the dimensions of the enlarged photograph, well, what we're going to do here is our original, our new length, that's what I want to say here. Our new length, is going to be equal to the original length multiplied by our linear scale factor. So that is going to be, 10 inches multiplied by 1.2. So it's going to be 12 inches. Our new width is going to be our old width multiplied by our linear scale factor. It's going to be 8 inches multiplied by 1.2, and that's going to be 9.6 inches, okay, at the end there. Now, finally, Maggie must also produce a print of the original whose area will be reduced by 25%. Determine the dimensions of the print to the nearest hundredth of an inch. Okay, well in this case here, our area scale factor is going to be, it's going to be, 100% of the original minus 25%, which is actually going to be 75% of the original. So this is the area scale factor, which means our linear scale factor is going to be the square root of that. Now, I know that that's not going to work out to be a really pretty number here, so I'm just going to leave it like that. The calculator can handle that anyway. So if I want the, let's say the length of the new, that is going to be the length of the old multiplied by the square root of 0.75, our linear scale factor. So that's going to be 10 multiplied by the square root of 0.75. So I'm going to have to do that one on my calculator here. So it's going to be 10 multiplied by the square root of 0.75. We get 8.66. The width of the new is going to be the width of the old multiplied by the square root of 0.75. So it's going to be 8 multiplied by the square root of 0.75. So same thing, 8 multiplied by the square root of 0.75, 6.93. Okay, so this really does look like it's the same question that we'd seen before. So in this question we read, Charo designs a Christmas decoration in the shape of a sphere. The sphere has a surface area of 200 centimeters squared, okay. She makes an enlargement, that's important, of the decoration with a surface area of 800 centimeters squared. What are the linear, area, and volume scale factors for the enlargement? Okay, so we're given a comparison between the two surface areas here. So our area scale factor is going to be, and it is an enlargement here, so it's going to be the area, I'm going to write new here. It's going to be the area of the new over the area of the old, and that is going to be 800 centimeters squared over 200 centimeters squared. And so the answer is just 4. So the area is multiplied by 4 to get, the old area is multiplied by 4 to get the new area. Now, that means our linear scale factor is going to be the square root of the area scale factor. This is going to work out beautifully because the square root of 4 is just 2. And now, because the numbers we're working with are so nice, remember that our volume scale factor is going to be the linear scale factor cubed, and 2 cubed is equal to 8. So there we go, area scale factor, linear scale factor, and volume scale factor. A circular amoeba's surface area is growing at a rate of 5, nanometers squared per minute. Now, or is that that's micrometer. I'm sorry, micrometer squared per minute. Determine the amoeba's surface area after 12 minutes if its initial surface area was 10 micrometers. Okay? Okay, well, let's just figure this out here. We know that it's increasing by 5 micrometers squared per minute. Okay, well, after 12 minutes, so we're going to take our rate, just to figure out how much it's grown here, we're going to start with its initial surface area, okay, the initial one, and we're going to add to it the amount that it has grown. So we're going to take its rate, okay, the rate, and we're going to multiply that by time. And that should give us our total area at the end here, or I should say our final area. Let's do it like that, our final surface area. Well, our initial one here is going to be 12 micrometers, sorry, 12, 12 minutes, 10 micrometers squared plus 5 micrometers squared per minute. And then that's going to happen for 12 minutes. Okay, so that's going to be 10 micrometers squared plus, well, the minutes here are going to cancel. Maybe I'll pull out a red here. The minutes are going to cancel here, and you're going to be left with 12 times 5 micrometers, which is going to be 60 micrometers squared. That is going to equal our final area. So therefore, the final area is going to be 70 micrometers squared. Now, what is the linear scale factor of the transformation? Now, I believe what they're trying to ask us here is how do we compare the original one here to the final one? So our linear scale factor is going to be the square root of the area scale factor. Okay, well, to get the area scale factor, and I'm going to just fit this inside the square root here, it's going to be the new area divided by the old area, which was 10. Yeah, for a second there, I lost track of what was going on there. It's going to be 10 here. So this will be the square root of 7. Okay, that was just kind of an ugly number. So let's figure out what that is, maybe to the nearest tenth here. So the square root of 7, so 2.6. So basically, we're going to multiply that by 2.6 times. Okay, the linear dimension. So for example, we might say that the radius of the original has now gotten 2.6 times larger to create the new one.